Hello, my people. Hope we're doing well today. As we discussed on Friday, this section is average function values and mean value theorem for integrals. I distinguish between the two, but basically, mean value theorem is sort of an implication of finding the average function value. So for most, if not all, of the problems we're going to run through, we're going to try and do both. Okay, some of those mean value theorem C values will be capable of being arrived at by hand. Some of them will be calculator based, and we'll sort of deal with that when we come to it. Now, when we're talking about the average function value, remember that this right here is how we find the area under the curve, okay, on our interval, okay, on A to B. So let's go ahead and I'll describe it kind of the same way that I did when we did it on Friday. Now, if you have a function and you want to basically find the average value from A to B, the first thing you need to do is you need to find the area from A to B. And then basically what you're doing when you divide by the width of the interval is you're basically asking yourself the question, if this area was a rectangle instead of having a variable height, right? If it was a rectangle and it had a constant height, what would that height be? So you're taking the area and you're dividing through by the width in the hopes of finding that average function value. Okay. And when you do find that average function value, when you find the height that area would be on that interval if you were to rectangularize that area, you're finding the average value. Okay. Now, notice that in this particular example, it intersects the actual function, right? The average function value intersects the function here. What the mean value theorem for integrals actually does for you, just like the mean value theorem for derivatives, it's an existence theorem. It guarantees you, and I'll use language that's reminiscent of the original mean value theorem, it guarantees you that there exists a C in the interval AB such that the instantaneous function value, if we can call it that, the instantaneous function value is equal to the average function value, okay? And there exists at least one, and what we'll see in the examples that we're going to do is that you can, in fact, have more than one. Just like when you did the mean value theorem for derivatives, the mean value theorem guaranteed that there was at least one place inside the interval such that the instantaneous rate of change was equal to the average rate of change. Here, you're being guaranteed, as long as f is continuous, okay, we talked about that on Friday, that there exists at least one value, there exists a C in AB, such that the function value at C, the instantaneous function value, is equal to the average function value, okay? Now, let's go ahead and move on and do some examples, okay? Because I think that's kind of where things really pay off. Let's say that I am given the function f of x is equal to negative x squared minus 2x plus 5, and we're dealing with it on negative 4 to 0, okay? Now, you should know what this looks like generally. It's a downward facing parabola, and if I wanted to, find exactly what it looks like, I would just do a little bit of completing the square in order to get it into vertex form, right? Basically group the first two terms, factor out the leading coefficient, sort of push the c value over to the side, and ask yourselves, okay, well, half of 2 is 1, 1 squared is 1. But when putting 1 right there, that's not really a 1, that's really a negative 1. So if I've subtracted 1, I therefore need to add 1 to compensate so that I do not change the value of the function, merely its form. And I can do that. Okay, now that is a little more specific in terms of what it looks like. It's a downward facing parabola, no stretches or shrinks, but it does have two shifts to give us a vertex of -1, 6. Okay, now so we kind of know what that looks like at this point. And so we know that the vertex is obviously at -1, 6. -1 is in this interval. So we're dealing with it where the parabola is at least partially, if not wholly, above the x-axis. So we're kind of thinking that we're probably going to get a positive area and therefore a positive average function value. Okay, well, if I went ahead and took this, and I'm gonna go ahead and put it in polynomial form because obviously in terms of integration that is the easiest form for it to be in, term by term and stuff like that. That would be the area under the curve, but we need 1 over b minus a in order to arrive at an average function value. Okay. And when we do this, negative x squared becomes -1/3 x cubed. The -2x becomes -x squared, and 5 becomes 5x, and we're going to evaluate them from -4 to 0. Now we need to go ahead and plug in 0, but it's going to be 0 minus 0 plus 0, so it's just 0. And then we need to start plugging in -4. Now when we plug in -4 into x cubed, 4 cubed is 64. It's an odd power, and therefore it keeps its negativeness. And so this becomes -64 times a -1/3, so it's 64/3. -4 squared, its negativeness goes away, and therefore it does not cancel with this negative right here, and it becomes -16, okay? And then, of course, negative into here creates a -20. And so we can simplify a little bit. If we go ahead and distribute like this, we can go ahead and arrive at -64/3 plus 36. And so we can, and you can combine these and then divide by 4. I find it much easier to do it the other way around. And that is going to be 27/3. 27/3 plus -16/3 is 11/3. Okay. Now, that is our average function value. Okay. Now, obviously, it was an area divided by 4, so it's pretty easy to determine the fact that the area from -4 to 0 was 44/3, but since we had to divide by its width in order to get the average function value, it's 11/3. Now, the question is, where, that would be our average function value, but if we wanted to apply the mean value theorem for integrals and ask ourselves, where on the interval is that function equal to that average value, we basically want, and it's probably best to take the Vertex Form version of the function and say it's -1 c plus 1 squared plus 6 is equal to 11/3. Now when I subtract 6 from both sides, I'm going to subtract it as 18/3 over here. Okay, and then that's going to be -7/3, but I have a negative over here that's going to turn that back into a +7/3, and therefore c is equal to -1 plus or minus the square root of 7/3. Now, that is 2 values, but only one of them exists within the interval -4 to 0. and that's going to be -1 minus the square root of 7/3. And I'm going to go ahead and spoil the surprise. That's -2.528. Okay, but I mean, getting to here, right? None of this required calculator work. Okay, it's only that last minute approximation right there. But you know, it'd be nice if we could go ahead and check our answer, and we will. Okay, let's go ahead and do that. Let me turn off the overhead lights so that I don't get any glare on the calculator. Let's go ahead and plug in -x², because I want to, you know, I don't have to do this, but I want to confirm. I know that that was my function. I know that this is my average value. Let's go ahead and go to the window. Let's go -5 to 1, because that will include the -4 to 0. I know that it's probably a little bit below the axis, and it also goes to 6, right? 6 is the maximum value for this, so we'll go to 7 on y max, and let's graph. Okay, so from -4 to 0, it's not wholly above the x-axis. We see there's a little bit of negative area accumulated between -4 and, let's say, you know, -3.4. But the vast majority of it is above the axis, which of course is why we get the positive area and of course the positive average value. Now, if we want to find this value right here, we simply need to calculate the intersect. Go ahead and go really close to it, press enter, it'll jump over to the other graph, press enter, and press enter a third time, and we're going to get 2.528 on our calculator, which is of course precisely what we got down here, -2.528. Okay. Alrighty, let's go ahead and do another example. Okay, let's try, and this one's going to be nice and tidy up front, but when it comes to the mean value theorem C values, we're going to need a little bit of help from our calculator. Okay, so we have a cubic function right there. I've given it to you in factored form. Okay, it should be really easy to figure out approximately what this looks like. You may not know the scale of it in terms of your y, but you should know that it's a cubic and it's positive leading coefficient, so it looks like that, right, because of end behavior. And it's going to have a 0 at 0, and it's going to have a 0 at 2 that has a multiplicity of 2. So basically what happens is this is going to come, and remember it's going to glance off like that. Okay, notice that I haven't scaled the y-axis because you still don't know quite what's going on there. I do, however, need to change the form of f of x if I'm going to use it for integration, because I'm going to need to do it term by term, right? And therefore 4, and I'm going to leave the 4 factored out because I don't want to get it mixed up in there. If it's a coefficient that is common, I can of course pull it out in front of the integral sign before doing the integration, and I risk fewer careless errors if I do that, because then I'm dealing with numbers that are a little bit tidier in the midst of my integration. So I know that my average function value is going to be 1 over b minus a from a to b of f of x dx. Okay, well that becomes, when I pull out the 4, it's going to be 4 halves, or 2, and then I'm going to just integrate term by term. I'm going to have 1/4 x to the 4th minus 4/3 x cubed plus 2x squared from 0 to 2. Now, that means that when I plug in 2 to the 4th is 16, divided by 4 is 4. 2 to the 3rd is 8. Times a -4/3 becomes -32/3. 2 squared is 4 times 2 is, of course, 8. And when I plug in the zeros, it's going to be 0 minus 0 plus 0. Isn't that fantastic? Okay, so I have 2, and then 12 minus 32 thirds. Well, 12 is 36 thirds. So 36 thirds minus 32 thirds is 4 thirds, times 2 is 8 thirds. My average function value should be 8 thirds. Okay? Now that is my average function value, and if that is all I was asked, that would be my answer. But, just to be, efficient with our time, let's go ahead and make sure that we just go ahead and do both actions for all of the examples, because first of all, can't hurt. But remember that if I ask you for the average function value, you are to stop here, which is why on all the examples I'm giving you that squiggly line, right? If I'm asking for the mean value theorem for integrals, I want you to take f of c and set it equal to that function value. And basically at that point you're saying, okay, Mr. Function, when is your instantaneous output 8 thirds? And I keep using instantaneous not for any real reason except to remind you of the parallels between the mean value theorem for integrals and the mean value theorem for derivatives. Now, this winds up becoming c minus 2 squared is equal to 2 thirds, and when I divide through by 4, and you could multiply both sides by 3 and then subtract 2. This, if you actually multiply it out, actually it's not cubed, that's squared. If you multiply that all out into its cubic, it's not going to give you a really nice and tidy sort of thing. So when it comes to this particular function, let's go ahead and say, okay, 4x minus 2 squared, and then 8 thirds. Let's go ahead and go back over to the window. I don't need, this is over in the negative x values. Let's go ahead and change this since I know my interval is 0 to 2. Okay, that's not what I meant to do. Negative 1 to 3. And let's go negative 1 to 5. And let's see what the function looks like. Function looks like that. And there's the average value. And notice that on the interval 0 to 2, it intersects twice. Now remember that the mean value theorem of integrals doesn't actually tell you what those values are. It merely guarantees that there's at least one. But in this particular instance, there's 2. And if we want to find those points of intersection, I simply need to find the points of intersection. So second calc. Let's do this one over here first. And we get 1.278, okay? And we'll go ahead and intersect the other one. And the other one is 0.207, okay? And those would be, if you said, 2 solutions, x is equal to 0, or approximately equal to 0.207 and 1.278, and that would be your answer, okay? Or actually, if you want to be C would be those, okay? So those would be your C values. Those are the inputs on the interval, or within the interval, where the function value is equal to the average function value on that interval. Okay. Alrighty, let's go ahead and stop there. I'll do a couple more examples on the next video. I may just do 2. I may do 3. I'm not quite sure, but as always, if you have any questions, please do let me know. Bye.